First of all, thanks everybody for being here. It's a great pleasure to be back to Tampere after 10 years. And also, I'm really happy to see the flexible technology blossoming and encompassing pretty much every area right now. So my focus today is to see how lots of, I would say, new technologies have converged, and they have enabled very new applications, not only in the conventional Internet of Things everybody has been talking about for the last 10 years, not only on Industry 4.0 and smart cities, but also lots of new applications, even in areas about cognitive sensing, about implantable, about even shape reconfigurable for the structures. That's a very brief overview of my team and what we have been spending. So today, mostly I will address something we call the 5S challenge. So talking about flexible hybrid electronics nowadays is not an issue having to do with materials, is not an issue having to do with electronics, is not an issue having to do only with antennas. We need to have scalable structures, structures that can very easily scale to the billions or the trillions, like IoT, sustainability. So how can you realize these flexible structures in a way that environmentally friendly, as well as requiring the least amount of power? More and more of these structures refer to zero power or near zero power, refer to consumption which is below at least microwatts or even below nanowatts. There are structures coming out with attowatt consumption when duty cycle. And then speed. You see an evolution of the frequency of operation of the flexible modules to at least 40 gigahertz now with 5G, 135 gigahertz with the 6G new standards, and even going to sub-terahertz really fast. There's a projection that I would say, the large majority of the flexible electronic heterogeneous modules will operate above 100 gigahertz within the next 3 to 4 years. And then security. So you could have great sensors. You could have sensors that can fold around, that can conform around surfaces, but you need to maintain security, especially for medical sensors. Lots of idea about implantable, about digestible, about sensors you may utilize in a variety of applications. But the moment they get hacked, your medical data or your product data become public. So you have to find ways to introduce some hardware-enabled token of authenticity. And also intelligence. And I'm not talking about intelligence with the meaning of just adding electronics or adding a microprocessor in this case. But given the new generation of machine learning and AI, we're slowly moving to an idea that the device itself will reconfigure, will change shape, will activate different areas in order to accommodate to new conditions. You would have a sensor operating for the walls of this room right now, but the moment somebody is walking in front, blocking the communication, most likely you will have to either change the shape of this sensor or activate different areas of the meta surface interrogating the sensor. And that's a 5S challenge. Now, also, if you look at the typical multi-layer flexible structure, you see another 3 or 4 more hardware-specific challenges here. Dies are becoming smaller and thinner. Everybody's talking about now chiplet-based integration. So instead of having some really large ICs, you have to create a cavity, embed it, wire it, and then here you go. quite soon you're going to have to synthesize with a Lego-based architecture of different chiplets. One chiplet will do the power management, another chiplet will do the radiation, third chiplet will more or less collect, analyze, and filter data from your sensor. And all of them now will be very deeply packed. Now, typically, whenever you're talking about flexible structures, you tend to think in terms of the Band-Aid or in terms even of a credit card. Now that we're talking about heterogeneous integration of chiplets, you're talking about structures that the space in between the chiplets, between individual chiplets, will be 3 to 5 microns. So the whole structure will be significantly smaller than 1 millimeter square. And you could have many, many sensors within this area. So it's going to be really important and also useful utilizing additive manufacturing to accommodate different dies. The second important point, especially for flexible modules, is how do you handle power and how do you remove heat? So you add more and more and more functionalities whenever you have your flexible devices, which means even if the individual parts have a very small power consumption, the aggregate power could be significant. And I would say the majority of the flexible materials do not have the greatest thermal conductivity. So more and more, the big challenge is how you integrate microfluidic channels, how you integrate structures that allow you to remove the heat without constant deformation. For most of the papers, I have seen you get your structure, you bend it, you show the flexibility. That's a great paper for conformal. But what's happening in reality is, number one, whenever you operate the structure for quite some time, due to heat accumulation, you would have plastic deformation. And then due to the flexibility, the shape does not come back to the initial state. And that reflects on the performance. And then the second case is, especially for wearables, if you want to estimate the performance of some flexible structure, you have to do many, many cycles. It's great to show in a paper or in some demonstration that you bend and unbend 5 times. But in practice, you may need some structures that work for 10,000 cycles, 20,000 cycles, 100,000 cycles. And that's where the problem starts. That's where the synergy starts of different parameters shown here. And also, I would say this shape changing is getting quite popular. So more and more times, you have flexible parts with flexible interconnects, we'll see at the presentation, and then the shape could readjust itself. So you would have kind of a flat sensor. And then due to blockage, the sensor could fold as a cube or could fold as a polygon in order to maintain some interrogation capability. Lately, as we're gonna see, with the emergence and the proliferation of the printed lenses, a new opportunity comes up. The opportunity of utilizing the ambient cell energy 5G signals from the base stations to charge your device. I mean, energy harvesting has been around, I would say, more than 12, 13 years for RF energy harvesting. The first papers came up around 2010. But this is the first time in the history of cellular communications that wireless power transfer is part of standards for 6G. If you check all these new standard committees for 6G, they do not focus only on realizing a system that transfers data. But slowly, we're moving to the era that the communication companies will be also power companies that will be able pretty much to power up IoT systems utilizing base station radiation beam. If you could summarize some quick specs for flexible systems that operate Internet of Things, we would say the Internet of Smart Skins. Now, smart skins that can be wrapped around not only the human body, but maybe walls, maybe buildings. You're talking about thin flexible devices. You're talking about devices that have a thickness maybe below 125, even 100 microns, that have a variable system of flexibility, ultra low power. The whole system should work with less than 20 microwatt. And I'm talking about everything. Here you see a typical integrated system where you have a sensor, you have a harvester. Here, solar cell could be electromagnetic. You could have a reflect array to be able to interrogate from different angles, and also some communication subsystem that will take advantage either through backscattering, through modulation, anyway. So the whole consumption should be ultra low power, below 20 microwatt. If possible, batteryless. Battery is one of the main roadblocks right now. There have been lots of printed efforts. And actually, I have seen even people attending this conference have done excellent work on batteries. But the big question is, what are you going to do with batteries after you dispose it? That's a major environmental issue. And also, that's an issue of wasted resources. Everybody's talking about resource getting scarcer. And then the next one, which has to do finding smart ways of extending the range. Many times, whenever we're talking about wireless sensors, the target is maybe interrogate with a cell phone, like 20 centimeters, 30 centimeters, and so on. But how about smart cities? If you have a smart city application or an autonomous car, having a range of 1 meter will not help. Everybody's talking about moving to self-driving cars with, let's say, level 3 to 4, which means almost complete autonomous driving. Now, to do that, you need to have long range for all of the systems. So 20 microwatts to 50 meter. Big, big challenge whenever you try to realize that. In addition to this, especially on structures you utilize, I would say, with soft, flexible systems or soft robotics. Now, whenever you have soft robotics with flexible sensors or flexible electronics, if you have soft robotics or if you have even smart surgery or remote surgery, ultra good localization, or as we call sub-centimeter accuracy localization, is really important. You don't need only the ID, you don't need only the data collection, you don't need only the good quality of wireless link, but localization is getting really, really, really important. And you will hear a lot about this. Even the discussion nowadays about 5G, you may have heard there are lots of different frequencies playing around. So there are 5G solutions between, let's say, 2 and 3.5 gigahertz. And pretty much that's a 5G you're using for your cell phone. But the question is, what's next? We said before something about 100 gigahertz. Now most of the systems are below 2.4 gigahertz. So there have been some ideas of extending to 24 to 40 gigahertz. In a sense, increasing the data rate by a factor of 10 to 15. Problem is that maybe localization, maybe electronics are fine, but it's very expensive. So now people are talking about 7 to 24 gigahertz, bringing down the frequency and so on. And then that's why I'm talking about centimeter accuracy. So the question is, can you have a sub-centimeter localization accuracy with a single reader, angular, and range? Because the other idea that would pretty much kill the operability of your flexible wireless sensors would be to flood the area with readers. Sometimes this redundancy is required, especially for logistics, in order to cover a large area like here. The question is, can you cover an auditorium like this with a single reader and then taking advantage of signal processing and AI to have a good localization? You'd be more compatible to metal mounting. And also a new term that has come up for flexible systems is something called self-healing. So what do I mean by self-healing? Most of the times, whenever you mount the systems for flexible electronics, flexible sensors, and so on, after some time, they start wearing off. due to aging. They start cracking. So you could either have metal cracking, you could have CNT electrode cracking, or you could even have some plastic deformation, which shifts the frequency. The question is, can you create some systems that can self-compensate? And that can be done based on the design of the electronics, the antennas, and so on. So these are structures that self-correct the performance, extending the life cycle for this case. Just some quick examples. We saw that. That's a full smart package with multiple features. That's a horn antenna integrated for multi-chip modules, and also biomem shown here. So if you look in terms of the historical evolution of flexible systems, I would say the story started around the beginning of 2000s with liquid crystal polymer. That was the first material that was very thoroughly investigated for applications all the way up to a millimeter wave. So that was a big step from printed wire-board. I would say till mid-2090s, everybody was using printed boards. Single layer, components placed far apart, not significant miniaturization. And then around, let's say, the end of the 90s, beginning of 2000s, people started taking advantage of third dimension. The first 2.5D structures, multiple layers on top of this, utilizing ceramics. And then early to mid-2000s, liquid crystal polymers start getting utilized here. Now, where do we stand today? It's a much wider variety of materials. Materials ranging from PET, carton, to fabric, to paper, and to glass. You will hear more and more and more, I would say, within the next 5 years about glass-based materials. Glass is quite flexible. Glass is very smooth. So you may realize now electronics in excess of even 200 gigahertz. That means very large data rates. You are going to have less imperfections, so loss is lower. But also, this is a new material. So the big trade-off is how to take advantage of the excellent properties of the glass, integrate with windows, integrate with windshield for your car, even integrate with your glasses to realize smart glasses or augmented reality. How can you do it in a way that will not be extremely expensive and also that will include lots of features? And all of these parts now are standard, 3D integration, MEMS integration, thermal, and nano. Additive manufacturing has enabled a quantum step in this case, because that has realized not only flexible electronics, as we call, but compressible and stretchable electronics. So you may twist it. Let's say you have some flexible electronics for some wind turbines, or you have some flexible electronics for helicopter blades. And now you can do it. And then the same thing for compressing or stretching. If you asked me about a couple of years ago, what is the typical stretching ratio before the performance starts getting bad? I'll tell you, maybe 2 to 1, maybe 2.5 to 1. But now, utilizing sharpened carbon flakes, you can extend this maybe 4 to 1, 5 to 1, 6 to 1. So that's a degree of freedom unprecedented. In addition to this, what we start seeing is, especially for sensors, you could create not only flexible sensors, but sensors with controlled porosity. Now, especially for gas sensors, chemical sensors, or biosensors, porosity is really important because it really controls the effective area and also the selectivity. So here's an example of some biconical porous sensor on a flexible substrate you may realize. That's some electronic on glass, 2 bow tie antennas connected to a sensor. You may interrogate with backscattering, and that's a printed antenna on top of the IC. In addition to what we said before, one part that stays sometimes under the radar is interconnect. Okay, you would have a flexible sensor. You would have a flexible antenna. You would have some flexible electronics or flexible solar cell. How do you interconnect for different radius of curvature? Now, most of the times, place wires, or you utilize a wire, a via hole you drill within your substrate. But what's happening if you have a via hole, or a metallized cylinder, or a wire whenever you bend it excessively? The via hole will crack, so will not work well. The wire will delaminate and fly over. So there's a new generation of interconnects, which is called the ramp interconnect. So based on the curvature, you may have slanted interconnects, not vertical interconnects, maybe angular interconnects, shown here. So utilizing these slanted interconnects, or as we call ramp interconnects, you can account for the bending, and then you have a performance which is identical or even better than conventional wire bonds or via holes shown here. Obviously, one of the most important points, even after you fix all of this, has to do with self-calibration. So you would have a great system, great interconnects, great sensors, but then you know very well if you're doing work on antennas or any wireless systems, the moment you bend an antenna, no matter how good your design is, you will be the best designer in the world, then the radiation properties change. Your beam starts getting broader, you have side lobes and so on. So the big question is, can you have a system that can self-calibrate and correct the phase in order to account for this? We're going to spend time on printing, just stressing the fact that now combining AM, inkjet printing, 3D printing, aerosol printing, gravel printer, pretty much you can print almost all materials, including die attachment, and you can add parts such as embedded through mold vias, the ramp interconnects we discussed, periodic FSS shielding, microfluidic channel, and so on. That's just a quick idea about this ramp interconnect we discussed before. So that's now getting, I would say, the most popular whenever you try to attach MMICs on flexible substrates. Or on the other side, utilizing 3D printing, now you may realize cavities on demand. So one of the other challenges, especially for flexible electronics, was utilizing subtractive technologies. The cavities had fixed size. Pretty much they had the size of the most common ICs, which made the situation difficult if you had some IC or some component that was not standard size. Now it's quite easy to print the cavity of the right size, no matter how small it is. We have print cavities like 3 micron by 3 micron for really tiny chiplets. You attach it, you mount it, everything goes there. And then this way, now you can start realizing even complicated structures. Here you have a Ka band, LNA, MMIC with the ramps, similar performance. Another important point for flexible structures is flexible radial interconnects. So the question is, what is happening if you have some flexible module that does not have a single phase, but has multiple phases? That's not rare. You could have polygonal shapes and so on, but the interconnect is really important. And I wanted to stress that that's one realization of effective foldable interconnect. That makes a huge difference. Most of the times, what people are doing is you have a straight line, 90 degrees, straight line, and so on. Doesn't work. The higher you go on frequencies, the more loss you have. So now there's lots of discussion and optimization, realizing some radial flexible interconnects that feature the same transfer coefficient for any bending all the way up to 180 degrees, as well as we call fully foldable hinge interconnects. So the question is, whenever you have, for example, two parts of your flexible sensor or flexible electronics, how you can fully fold it in the form of a bracelet, how you can wrap it around some machinery, how you can tilt it for different ways, especially for deployable structures that can be launched in space, autonomous cars, and so on. Backscattering is getting quite popular. This has been a technique well known for people in electromagnetics, but actually now it's getting popular outside this niche group of people. And backscattering means you don't have a power source for your sensor, for your flexible mode. You can either backscatter the energy of some handheld device, like a phone or nearby FM station. So this is called like opportunistic backscattering. Radio waves, TV waves are around. So based on the way your sensor scatters this energy and then detects by your cell phone or a low-cost software-defined radio, you're going to have quite good performance. I mean, we're talking about gigabit per second backscattering data rates with a power efficiency below 0.15 picojoules per bit, 1 kilometer plus interrogation range. Actually, in one experiment with some university in Scotland, people utilize energy from Glasgow FM radio stations to read sensors at distances of more than 6 kilometers. Here's handheld, different idea. So most of us are holding a phone, and the moment you communicate with Wi-Fi, you transmit some power. This one is utilized to backscatter from wearable sensors, then collect them at some point, transmit to software-defined radio. And this one is backscattering from an overflying drone for smart agriculture, utilizing just an RF switch in this case. That's to monitor some crops as well. Just an example of the simplicity of these backscatters, you just have some switch here and some flexible printed array. That's for 24, 28 gigahertz, 4 gigabps, and also you have the capability of different modulations, ASK, QPSK, and so on. AI has been the major key enabler, especially in the processing of the data. Because one of the big questions is, you have a great flexible sensor, and actually you have a great constellation of sensors, thousands, tens of thousands. Now, how are you going to do the processing without needing a power station? So what we have seen, and the reason I chose this is just to do some suggestion, the decision trees and k-nearest neighbor are a good starting point if you want to start utilizing machine learning for your flexible sensors. There are many more advanced algorithms, but I would say both of these algorithms are a very good starting point. You can acquire some quite good control of using them within a month or a week. So it's a good starting point, and then after you start getting some preliminary filtering, preliminary good processing of your data, you can move to more advanced ones. And we have seen, if you have no assumptions, which means the preliminary deployment of a flexible sensor in a new environment, you start with decision trees. And then whenever you have some pretty good idea of the local maxima and minima, you go to k-nearest neighbor in order to narrow down to the optimal solution, improve the sensitivity, and so on. What's interesting is additive manufacturing has reached now a point of fully printing multi-layer modules. Here's an example of how you can print a 28 gigahertz backscatter FHE-Enabled sensing 5G module. And you see how it goes. You 3D print the substrate with the holes, inkjet print SU8 for planarization, print the interconnects either this way or ramp, fill the cavity, and the cavity does not need to be rectangular. So you may realize any type of cavity for your sensor that works, sometimes for some structures, some gas sensing for aerosols and all these things. The rectangular cavity is not the optimum, doesn't matter. You may realize any type of shape. Here's a trapezoidal cavity. Fill it, print the antenna, and so on. So slowly we're moving in an era that multi-layer flexible components is possible. Now, you would ask me the question, what is the biggest challenge? Okay, you're telling us that you could have 4 layers, 6 layers, 8 layers. But everybody knows the more layers you add, the less flexible your system gets. And even if you have very thin layers, still, reliability becomes an issue. So there are 2 major challenges anytime you have this. One challenge is the different thermal expansion coefficient of the different layers. So if you have different power, you have local deformations and possible delaminations. And the second is surface roughness. Different materials have different surface roughness. The answer is, believe it or not, surface roughness has gone lots of ways from the 3D systems 5 years ago. Whenever we were talking about 3D, let's say before COVID, typical roughness was quite large. I mean, larger than 1 micron, even 10 microns sometimes for the really low cost 3D printers. Now we're talking about surface roughness of 0.1 micron, which makes it quite efficient whenever you have some practical systems. And then the other question for thermal expansion coefficient, more and more times, what you see here is you print thermal vias. So whenever you have the thermal vias, you don't overheat the interface between the materials with different CTEs. And then that's how we have managed to go all the way up to 6 to 8 layers, maintaining the same flexibility. But I want you to keep it in mind, these are the 2 major issues, like mismatch of CTE and also roughness. In addition to this, now you can realize multi-chip modules utilizing additive manufacturing. Here you see an example where you can print even the PCB. And the reason I'm saying print PCB is because you can slowly, fully print now the flexible materials. And then based on the air intake, you may control the flexibility in these materials. So you may replace PCB here with any flexible material you have in mind. Could be Teflon, could be PET, could be some thin glass, or even lately, I mean, you will hear more and more about this. There's this new material called aluminum ribbon, aluminum ribbon ceramic, or AR or ARC materials. You hear more about these ARC materials, especially for high power systems. So now I'm switching gears and I'm going away from IoT possibly to some electric car, wireless charger of an electric car. And that's why talking about these ARC materials, flexible materials that have a really high thermal coefficient. That's some example of some integrated flexible module on glass, where you have the core of glass, and then you have some additional layers on top and bottom of glass, really flexible. This one operates pretty much for the whole 5G at 40 gigahertz. But just want to show you a typical architecture of flexible glass-based modules. This has, I would say, an efficiency at least 20 to 30% better than conventional materials. And now it becomes available because the next question you could ask me is, you're talking about glass, but obviously you're not talking about glass for the windows. But now there are companies, you can get very easily flexible glass samples, and that's why this one has started proliferating. Transparent, different properties, and so on. And also the other idea for flexible is now applying origami principles now to change the shape. So the question is, okay, you have flexible faces, but then the question is, can you utilize tessellations, utilizing folding of origami structures to change the shape, taking advantage not only of the flexibility of every face, but also the flexibility of the hinges and the flexible interconnects. Here you see an example of origami foldable prototype for frequency selective surface, where you can switch the frequency, but also you can switch the polarization. So by just folding to one direction or to the other direction, you can modify polarization as well. So you have frequency, polarization, reconfigurability, just folding and unfolding. The other advantage is taking advantage of the origami structures, you require the least amount of power to fold. Now, this is a parameter very few people pay attention, but if you think that the flexible structures of the future will be large area, the amount of power that takes to fold or unfold, flex or unflex, will become quite significant. You're not talking about a tiny unit cell, you're talking about a whole wall to start maybe bending or flexing. Think about the new generation of sensors wrapped around the fuselage of an aircraft. So in this case, the amount of power to bend or fold or unfold becomes quite significant. That's how we chose origami principles, because it has been proven mathematically that that's the least amount of power required to change the shape. Another idea of fully 3D flexible structures is shown here. We call like the flexible antenna trees. And this is not the typical flexible planar structure here. So the question is how you could have some flexible antennas or even flexible sensors in fully 3D. And the answer is just utilize flexible porous scaffolding. So you print the scaffolding that's called Voronoi structure. Voronoi was a mathematician correlating the stiffness with the porosity of 3D structures. So based on the gaps here and the pore size, this one could be very stiff or not stiff at all. And then you can then wrap around, for example, a helical antenna, a zigzag antenna with liquid metal and so on, and then compress and decompress on here. So this is a technique to extend the flexing, not in 2D, that most of the times people are thinking, but also 3D shown here, utilizing this scaffolding. Just a fun graph to show the evolution of the papers on flexible electronics. You see in 2000, there were like 10, and now we're talking about thousands. So that shows how proliferation has taken place. Now, the other question I would like to discuss a little bit is scalability. So how you can realize large area and fully scalable flexible surfaces. I mean, there's lots of hype about reconfigurable intelligent surfaces. Now, I would say like most of the people in flexible area are talking about reconfigurable intelligent surfaces or flexible sensors or flexible wearables. Buzzword, you go next week to APS conference, I can bet there are like more than 500 papers talking about RIS. Although I would say 90% of them are completely non-realizable. So the question is how you can make it happen. And the moment you're talking about large area, you have two competing factors. One factor is you have a very large area to cover. The other factor is in order to have some good performance, especially operating in microwave frequencies, you have to have a very good detail. So in a sense, you have fine detail for a very large area. That's the worst case scenario whenever you want to fabricate something. And that's how tile-based approach is really important. So in a sense, you synthesize the area utilizing flexible tiles. You may have some individual tiles, for example, with subarrays, beamformers, and sensors, and then you have some mounting scaffolding. You can place one next to each other, like this one. And then you may grow it as much as you want. And you can see you maintain flexibility, and if even the individual face is flexible, this one can be even a larger area of curvature. And then in this case, you maintain good performance of the system on the individual tile level, but you can create any area you want. And the other important point is the healing we discussed before. Now, typically, if you have an RIS, a very large area you have created, if one component breaks, if one diode breaks, you have to change the whole system, which is quite ridiculous. I mean, instead of replacing a diode costing $2, you may need to pay like $10,000 to replace the whole area, demount it, fix it, put it back. Now, using this tile-based approach, you just remove the tile, replace with an identical tile, here you go. And then that works quite effectively. And coupled with the phased array in our system, you can have beam tilting, beam direction, beam redirection quite effectively. And that's some more detail about the tiles, talking about the flexibility around the fuselage, around the bending for different directions, implementation for RIS. Now, this is the next step. Something I believe will be the next big challenge for flexible electronics we discussed before, chiplet-based. So the question is how we can go from the dimensions we discussed before to dimensions of chiplets for 70 gigahertz plus, 15 times, require 15 times smaller loss and parasitics, and a very large number of interconnects. It's not straightforward. It's not just scaling down the dimensions. You're talking about a really large fan in, fan out, 50, 100 plus interconnects. And it has to be robust. So in this case, you do not have one interconnect of your sensor to your IC to your antenna. You have 50 lines, 100 lines in an area which is smaller than 1 millimeter square, shown here. And you have to do it for chiplets of different technologies. Now, most of the times we're used to utilize silicon. I would say most of the ICs are silicon-based, but we're moving to the era of heterogeneous integration. So you have one IC which is gallium arsenide, one IC which is indium phosphate, one IC which is silicon germanium, and then all of them packed next to each other. And then you have to have interconnects here. And now that's why I started covering the issue of interconnects of the ramp interconnects, or as we call the pillar array interconnects. So you will start seeing for this new generation, very new interconnects. For example, you would have vertical pillars. It's called like the pillar array. You could have pillars, each one with dimensions of like 5 micron, spacing 5 micron, 100 of them below your IC. And these vertical pillars, which is, I would say, the evolution of ball grid array technology, this one will allow you to have a flexible system with all of this operated. But I would say this is kind of a projection of the future whenever chiplets start getting reality. Now, the other issue I discussed is calibration. So talking about flexible systems, you have different bending. And I would say the typical perturbations of flexible systems can be divided in 3 different types. One is rotation of the faces. The other is shift, which is happening whenever you stretch. And the other is twist. So these are the 3 different ways that your flexible system can change shape or can require calibration. And like 2 faces here, you see that's a typical rotation at this point if you have a bracelet around your arm. So what we have seen is, believe it or not, even utilizing the camera of your smartphone, the stereoscopic camera, and then processing it, coming out with data sampling, you can obtain the bending, and then you can come up with some phase correction system. So that's something called computer vision calibration. This is getting quite popular, utilizing stereoscopic camera, obtain information about this flexible electronics, then apply some correction signal in this case, and then pretty much have some performance quite close to pre-bend. The other idea is something we call flex compensation utilizing a backside sensor. So just to give you an idea, I know all of you know that, but just for some information. So let's say you have some antenna array that in the flat area, you have a main beam point in a specific direction. That's the direction of your gateway. And then you wrap it around your arm. It's kind of a bracelet. Now you see the new radiation pattern. What do you see here? That instead of sending all your power to the direction you want to send, you're wasting it over a wide area, creating interference to the neighboring sensors. So you need to correct this. And the idea is place some sensors on the backside, apply some correction phase, and then you go back to the initial state. And this is quite important now, especially talking about phase duration of multiple sensors and talking about far range of interrogation. Again, utilizing LDA, linear discriminant analysis, you have a better than 90% accuracy in this case. Just some more about shape morphing antennas. The reason I want to stress now about phased arrays is flexible electronics inherently add degrees of freedom. So in a sense, we can harness the bending now to create some antenna arrays with almost limitless reconfiguration, as we call limitless on-demand reconfigurability states, utilizing this origami we said before. So having this type of unit cell and bending, pretty much doing selective activation, you have limitless tessellations. So utilizing one antenna system, you would have 1, 2, 10 beams, and so on. And just show an example of the shape changing of this type of origami antenna. And this one actually is getting automatic. So by developing some lookup books and then saying, I want to have a radiation pattern which has this beam go to this direction, this at lobe level, the system changes by itself the shape. So now you start seeing intelligent, flexible systems that change their shape to accommodate different conditions, radiating along this direction, radiating in 4 directions, radiating in this direction as well. And just to show some prototypes. So the reason I'm showing this prototype is not only to show it's flexible, we have seen lots of flexible systems here, but to see the new type of interconnects and feeding. So we're moving away from the straight lines. Straight lines were the typical flexible components, I would say 5, 10 years ago. Now you have to adjust to this case. What I want to show is the next one, which is something called camera-inspired, lens-based, zero-power metal surfaces, utilizing, as we call, RF pixels. So the idea is, how can you have some type of a flexible system with a radius of 80 micron and a broad angular coverage? So the reason I'm showing that is to show another big challenge for flexible systems. And this is the challenge of range and angular coverage. Now, typically, if you are close to your gateway, you would have quite wide angular coverage based on the sensitivity. But the further out you go, this one is getting problematic. So this case, instead of having antennas, you could have some concentric plates, as we call RF pixels, that respond to different directions. And that's how they can enhance this case. The other interesting point for flexible systems is not only the localization, but also the orientation. So one of the questions is, okay, you have this flexible component, this robot. And you have a pretty good localization. You know, the robot is at XYZ with an accuracy of 1 centimeter. You can get the sensing, you can get the data possibly from haptic interfaces for this. But there's a big question, and there's a big difference. If the arm of the robot tries to grab a glass like this, like this, like this, or like this. So orientation detection of your flexible system is also becoming quite important. Now, somebody would say gyroscopes have been around for years and years and years, but it's not so straightforward to integrate with a flexible system. So what has come up quite recently is some MMID gyro. So utilizing RFID technologies and then utilizing 4 antennas, each one rotated by 15 degrees, and taking advantage of the phase difference between these 4 antennas rotated by 15 degrees. So you see, this one is 15 degrees off this direction, 30, 45 degrees. Now you can see that at least up to 9 meters, you have some pretty good capability of detecting pitch, roll, and yaw. So the reason I'm showing that is to show that the new generation of flexible systems are not satisfying only one purpose. In the beginning of the flexible systems, people were focusing only on sensors. They're focusing only on antennas, focusing only on RFID tags. Now you have a convergence, and you have a convergence of communication, sensing, localization, orientation, detection. And I'm going to spend lots of time just to show you the practicality of KNN AI algorithm I saw before. So you train your system, utilizing amplitude response and phase response, and you could have a pretty good accuracy shown here. Just to show an example of a wearable flexible system that's a smart bracelet, UWB based, where these are the different components. Almost all of them are printed except from a copper tape for simplicity. This has been tested for a medical company in the States. That's wearable. You have UWB array of circular ring antennas. You have a beamformer. You have some sensors. That's a magnification shown here. That's on PET. So now you can see that you do not need expensive materials. PET is pretty much a flexible material that you can find on your beverage containers here. What I want you to see is this now, because again, that's I'm looking at the future. So that's what we have today. You would have 3D printed microfluidic channel to sample some bio liquids. You would have the IC, you would have the antenna and so on. That's today. But looking at this graph, I don't know if you can see the dimensions here. And that shows the next step of additive manufacturing. Now, if you look at this one, this is 1 micron, and this is 80 micron. So slowly we're moving to the era utilizing just 3D printers, and I want to stress that, you could have high aspect ratio antennas, and also very dense pillar array for interconnects. Each one of them is 1 micron, 0.1 micron, 1 micron, 0.1 micron. And this is also a spiral here. So talking about migration to 200 gigahertz, 400 gigahertz is not an expensive sport anymore. Now, till I would say a couple of years ago, spending time on terahertz or sub-terahertz was considered to be really expensive. You need really expensive equipment. And now the question is, do you still need a Ferrari to drive in the road of your neighborhood? And the answer is no. I mean, this one has been produced with a 3D printer that costs like $10,000. So you will see more and more talking about sub-terahertz flexible systems that can be quite practical and that can be fabricated utilizing low-cost 3D printing. shown here. And that's a big quantum leap, if you think about this. Because, as you know, for the sensing community, the smaller dimensions, the better sensitivity. The closer you can bring your electrons, the closer you can bring your fingers, the more miniaturized the cavities you make, then you have a better sensitivity. So now we're moving to this era. And there will be more challenges. The biggest challenge, especially for flexible systems, is now a bending of 1 centimeter, which is considered to be quite extreme bending, will be really big for components being 1 micron apart. So it's going to be difficult. But on the other side, you may detect now so small bendings that you would have, in a sense, a better control and a better sense of bending than your arm. And that will move to a new generation of soft robotics shown here. And I will close with a couple of slides about 6G, because there's lots of discussion here. So what are the driving trends? More bit spectrum reliability. We're moving from area to volumetric spectral energy efficiency. So now we're moving to bits per second, per hertz, per joules, per meter cube, talking about fully 3D structures. So slowly you have to start thinking of your flexible systems, not as a planar sheet, but a 3D structure shown here. Smart surfaces, massive availability of small data, and that's quite interesting. End of the smartphone era. Now, what do I mean by that? What is the more power consuming part for your cell phone? What do you think? The screen. So what would you do to minimize the power consumption of your cell? Eliminate the screen. And believe it or not, now most of the major communication companies want to eliminate the screen and replace with a holographic projector from a bracelet. I'm not saying that iPhone 15 will have this, but you will see within the next 5 to 7 years some implementations with holographic projection from a wearable than a screen. Because that's the only way you can bring down the consumption to a level you can start replacing the battery, shown here. And I'm not going to spend time on numbers. In the slides, if you want, I have some ideas about, let me see if I have this, the rigid flex RFPCBs. There's lots of discussion, especially for radar or multi-standard systems. So trying to utilize some rigid PCB and then this flexible interconnect. Now it's becoming quite common. I'm not spending time because Qualcomm, Intel, all of them are doing that more and more. And but I want you to be aware of the rigid flex, and that's how it falls. So serpentine interconnects, rigid flex interconnects, fully foldable in the form of the accordion to realize multi-band filters, to realize multi-standard implementations, to realize components like this. And I will close with this because that's a fun. I promised somebody yesterday I would show some leaf sensors. So we were walking yesterday in the forest, and in a sense, if you think about this, that's a smart agricultural sensor that was created as part of an undergraduate student. So the idea was how you can monitor soil moisture and leaf wetness utilizing paper-based electronics. You can see this is a soil moisture interdigitated sensor. That's a leaf wetness, and also that's insect pheromone detection sensor to detect the leaves. And the third leaf shown here, this S antenna, you have a long antenna which gets energy from the local TV station, and then this one transmits to gateway. The last slide I would like to show is this one, and I will close. And that has to do with powering. So lately, there has been a big progress on utilizing printed lenses to power up a system. That's a printed Rotman lens you can integrate with your sensor, and then you can receive opportunistic signals from base stations at 5G around you. That's why I want to show this, because that was utilized actually in the formation of some standards for 5G for flexible systems. So this is kind of a credit card. That's a printed Rothman lens connected to antennas, receiving energy from different base stations, converting to an RF combiner, DC combiner, and now you start having 0.25 volts with harvested power here. So this is one way of tackling now some lens-based wireless charging of your system, replacing the battery as well. With this, I would like to close. Thanks for your attention. Feel free to ask any questions.